Okay, so our next talk is by Tomoshige Yukita, who was talking about growth rates and spectral radius of Coxeter groups.
Thank you for the introduction. Can you hear my voice?
Yeah, we can hear.
Okay, so I would like to thank the organizers for giving me the opportunity to give a talk here. Okay, so I will talk about the continuity of growth rates and spectrality of Coxeter groups. And I will start with the definition of Coxeter group. So a group G is called the Coxeter group if G has the following group presentation. So this means that each generator is of order 2, and the product of two generator Si and Sj is of order Mij. And here, if Mij equals to infinity, we omit this relation because that this means Mij equals to infinity means that there are no relations between the generator Sa and Sj. And the related objects to Coxeter group G, one is the Coxeter matrix, and the other is Coxeter diagram. And Coxeter matrix M is defined to as follows. So M is n by n, says symmetric matrix, and Ij's entry is defined to be the Mij. Here Mij is the order of the product of Si and Sj. And the Coxeter diagram is a labeled graph defined as follows. Its vertex set is S. Here S is the generating set of Coxeter group G. And if two generators Si and Sj has order Mij, here Mij is greater than or equals to 3, we join two vertices by an edge with labeled by Mij. So this is an example. So consider this Coxeter group generated by 3 elements, S1 and S2 and S3. And the product of S1 and S3 has order 3. So in Coxeter matrix, this means that this entry is 3. And in diagram, S1 and S3 is joined by an edge and by labeled by 3. And S2 and S3 has the product of S2 and S3 has order 3. This means that the entry here is 3. And in the diagram, S2 and S3 is joined by an edge labeled by 3. And in this presentation, S1, S2 has infinite order. So that we omit such relation. And in the Coxeter matrix, these two entries infinity. And in diagram, S1 and S2 is joined by an edge labeled by infinity. And the one related object related to Coxeter group G, which is called gram matrix. So gram matrix is also an by n size symmetric matrix. Symmetric. And Ij entry is defined to be minus cosine of pi over Mij. Here, of course, Mij is the order of product of Si and Sj. And by using the gram matrix, using the signature of gram matrix, we can divide the Coxeter group into 3 cases. One is called elliptic. So if Coxeter group G is elliptic if the gram matrix is positive definite, and is called affine if the gram matrix is positive semi-definite, and non-affine if otherwise. Okay, and now we'll go to the definition of growth rate. Let G be a Coxeter group, and S be a Coxeter generating set of G. I forgot the explanation of Coxeter generating set. So Coxeter generating set S is a generating set of Coxeter group G. which gives the group presentation like this. Okay, so for an element x, g, we denote the word length with respect to s by absolute value of x. And beta gm denotes the number of elements of G whose word length is at most m. And this is called growth function of GS, growth function of GS. And the generating function of beta Gm, the formal power series of this, is called the growth series and is denoted by Fg there. And the growth rate of G is defined to be the limit sup of m square root of beta Gm here. By using the Cauchy-Adamar formula, Cauchy-Adamar, we see that the radius of convergence of the growth series is equal to the reciprocal of the growth rate. And by using the growth rate, we can characterize the elliptic or affine Coxeter group and non-affine Coxeter group. So if Coxeter group G is elliptic or affine, if and only if its growth rate is equal to 1. And the Coxeter group G is non-affine, if and only if the growth rate is bigger than 1. So I would like to explain the motivation of this law, so which is coming from the convergence theorem in H2 due to Freud. Let A1, and AN be integers bigger than or equals to 2, and we allow that A1 equals to infinity or AN equals to infinity. And let us denote the delta of A1, AN, by hyperbolic anagon with interior angles pi over A1 and pi over AN. So this is the schematic figure. So this denotes the hyperbolic triangle. So like this interior angle is pi over 3. This corresponds to pi over A1. And this interior angle is also pi over 3, and this corresponds to pi over A2. And here, the two edges intersect, meet at a point boundary at infinity. This means that A3 equal to infinity. So we can write this hyperbolic triangle by delta of 3, 3, infinity. And we denote the hyperbolic reflection group associated with this delta by G of A1, that's AN. And it is known that G is the Coxeter group generated by the reflection along the edges of delta. And the relations are coming from interior angles of delta. Here, this denotes the hyperbolic triangle with K infinity. Yeah. And the reflection group associated with this delta has this group presentation. So the reflection along this edge is denoted by R1, and the reflection along this edge is denoted by R2, and the reflection along this edge is denoted by R3. Then the relation is coming from these interior angles. So the product of R1 and R2 has order K, and R2 and R3 has order K, and R1 and R3 has infinite order. Then Freud showed that if the interior angles converge to some numbers, then the growth rate is also converges. So it means that if K tends to infinity, we get the interior angles become smaller and smaller, and finally we get ideal hyperbolic triangle in H2. This corresponds to infinity, infinity, infinity. Then the growth rate here, omega G33, is the growth rate of this Coxeter group. Then omega G K infinity converges to the growth rate of limiting Coxeter group, omega G infinity, infinity, infinity. This is the result. This result is due to Freud. And in order to explain my result, I will introduce the space of marked groups, which is defined by Grigorchak. So the space of marked groups denoted by Gn is set of all pair Gs, where G is a group and S is a generating set of G, where the number of S is equal to N. Then Grigorchak defined the Ulton metric on Gn and showed that Gn is a compact metric space. It is important that the following, this condition holds for the metric T. So it means that, okay, let's take two marked groups, GS and HT. If the metric between two marked groups is less than or equal to 1 over E to the R, if and only if the metric fall in Cayley graph of GS centered at the identity and of radius R, and that of in K graph of HT is isomorphic as labeled graph. And I will introduce a space of Coxeter groups Gn. So this is a space or the set of Coxeter group G, or a set of the pair of Coxeter group G and the Coxeter generating set S. And of course, the number of S is equal to N. And I would like to talk about the topology of Gn and the continuity of the growth rate omega and the continuity of the spectral radius of rho. So I will first show that Gn is compact in Gn. Okay. So since the Grigorchak showed that Gn is compact, so it is enough to show that the space Gn is closed in Gn. Okay, suppose that the sequence of Coxeter groups GK and SK converges to some marked group GS. Here, this means that this is a finitely generated group, and this is a finite generating set of G. So in order to show that the G is Coxeter group, the following characterization of Coxeter groups is fundamental, so-called exchange property. Okay, let G be a group and S be a set of generators of order 2. This is very important. So the following are equivalent. So one is the pair GS is a Coxeter system. Here, Coxeter system means that G is a group and S is a Coxeter generating set. And the second condition is for reduced word W, which is expressed as S1, that Sn in G, and take an element S in large S. And if the length of SW is less than or equal to LW, then SW can be expressed as follows. This property is called the exchange property. Okay, so I will explain how to prove the result. So fix S and there is reduced word W in G. Here G is the limit of Coxeter system, GK and SK. Then by definition of the metric on the marked as a space of marked groups, we can find that some number K and the large R such that the fixed reduced word W and SW are contained in the metric pole in the Cayley graph of GS of centered at identity and of radius R, which is isomorphic to the some Coxeter group, isomorphic to the ball in the Cayley graph of GK and SK. Okay, let us denote the isomorphism between these two balls by alpha. And suppose that the length of SW is less than or equal to W. Then, okay, start with SW. By using the isomorphism between these two balls, we have this equation. This is in GK. And the GK is, we already know that Coxeter group. So we can use the exchange property because alpha is isomorphism between the two matrix balls. So L of L alpha of, okay, so this, the length of alpha of SW is less than or equals to L of alpha W. Since that, so we can use the exchange property in GK. We get the alpha of SW can be expressed as follows. And then by using the alpha inverse, so first we use alpha and again use alpha inverse, we get this expression. So this means that we showed that group G and S satisfied exchange property. So we see that the group GS is a Coxeter group, and hence this means that Cn is closed in Gn, and Cn is compact. And again, we prove the continuity of the growth rates of Coxeter groups. So the growth rate is a function of the space of the space of Coxeter groups, and it is continuous. But I don't explain the proof in detail. I will explain some example. Let's take a Coxeter group defined by this diagram. So this means that if we label it as follows, here S1, here S2, here S3, and S4. The group corresponding to this diagram is generated by S1, S2, S3, and S4. And the relation, so, for example, if we see that here, here, these two nodes, S1 and S2, is joined by an edge without label. Without label means that okay. Here means that 3. So like this. And if we focus on this edge, we get S2, S3. And here, this is an important point. So the relations between S3 and S4 is expressed as follows. And if we tend M to infinity, so goes to M infinity, we get this diagram. And this diagram corresponds to the limit of this Coxeter group. This is limit of this Coxeter group. And for Coxeter group, there is no, so how to say, let's say, so the growth series of Coxeter group can be expressed as rational function by using what's called Steinberg's formula. These two formula means that this is a growth series of GM corresponding to GM. And the right-hand side denotes the rational function. I don't explain in detail, but I would like to note here that the difference between these two expressions are only coming from the relations corresponding to these two edges. So here corresponds to this relation, and here corresponds to this relation. So by using this identity, we can see that this rational function converges to this one on the unit disk, and it's normally. This tells us that the growth rate also converges. By using same argument in general case, we can show that the growth rate of Coxeter groups are continuous. And last, I will explain the spectral radius of Coxeter group and its some convergent example. So start with simple random walk on mapped group GS. So here G is a group, and S is a finite generating set. Okay, then simple random walk on GS is a random walk on the Cayley graph of GS, defined by the transition probability matrix P, where each entry is defined as rows. Roughly speaking, this means that if the walkout moved from X to Y with the probability 1 over number of the element of generators. So in this case, this means that the number of S is equal to 4. So that the walkout moved from X to Y with the probability 1 over 4 at each step. And let us denote the Pn of xy, the probability that the worker started from the x will be at about xy after n steps. So for example, start with x after n step. Probably we moved from x to y after n steps. Okay. Then the spectral radius of GS, denoted by rho GS, is denoted by limit suit of n square root of Pn of E and E. So this means that Pn E is measures the probability that the worker move from the identity of G and go back to the identity after n steps. Roughly speaking, rho GS measures how fast decay the probability, this probability, and of course this quantity measures how rho GS measures the complexity of the Cayley graph of GS. Okay. And I will explain one example of convergence of spectral radius of Coxeter groups. So take a hyperbolic n-gon having the same interior angles. This means that, for example, take a hyperbolic 4-gon with pi over m and a pi over m and a pi over m, like that. In this case, this denotes by So the latter corresponds to delta 4 and m. And we also denote G and m, the reflection group associated with delta m. So I don't prepare the example, but I would like to note that Gn of infinity is isomorphic to the free product of n copied of Z2. So because let us consider ideal hyperbolic triangle. So this means that here 0, and 0. this tells us that the group generated by 3 reflections has only the relations of this kind. And this is isomorphic to 3 copies of 60. Okay, so then by, we can show that the limit of, sorry, no, this is not M. Here is M. Here fixed number, let us fix N, and if M tends to infinity, we get this convergence in the space of Cox group. And also we can see that the spectral radius is also convergent too. Probably this is the first, first result concerning the behavior of the spectral radius at the infinity. So the proof is heavily dependent on the result due to Harry-Keston and Dvorak and Moha, because they showed that the spectral radius of G and M satisfies following inequalities. And this value is exactly the same as the spectral radius of the nth copy of Z2. So that if we tend M to infinity, we can easily see that the desired convergence. And last, I would like to explain which works and the problems. So one is the set of hyperbolic or relatively hyperbolic Cox groups is crossed in Gn. So I mean that. So at first of this talk, I divided the Cox groups in 3 types: so elliptic, affine, and non-affine. And we can show that the set of elliptic or affine Cox groups is closed in Cn. And the set of non-affine Cox groups also closed in Cn. But we don't know how about the set of hyperbolic and the relatively hyperbolic Cox groups. But conjecturally, I think the hyperbolic Cox groups or relatively hyperbolic Cox groups are closed set in Cn. And probably the limit boundary of the hyperbolic Cox groups is equal to the relatively hyperbolic Cox groups, I think, but I don't know the proof. Okay. And concerning the hyperbolicity or relative hyperbolicity of Cox groups, knowing it is some conditions is known. So one is due to Musa, and for the relative hyperbolicity, the Kaplan showed that necessary and sufficient conditions. Okay, the second problem is determine the minimal growth rate for non-affine Cox group. Non-affine, because the growth rate of elliptic or affine Cox group are always 1. And the maximum growth rate is always n-1. So the interesting is the minimal one. And the problem 3 is the generalized results about Cox groups to the Artin groups. And for the problem 4 is the spectral radius is proves that the spectral radius is continuous. In the last page, I will provide some evidence. And the last, if Cox groups GK converge to the other Cox group G, how do geometric objects associated with GK changes? So for example, the Davis complex related to GK, or its geometric realization related to GK. Okay. So I will stop here. Thank you for your attention.
Okay, let's thank the speaker. Are there any questions?
I have a question, but maybe if you're around after Robert's talk, we could talk during the break because we're a bit out of time. Will you stay for one more half hour? My quick question that I want to talk more deeply about is the theorem on page 11.
11.
And I really wonder if this is true for other classes of groups. And the only results that I know are about Bohm-Sag-Solitar groups. The BS1n's limit to Z reach Z. And we know all of the growth formulas for those. So I wondered if it's true in that situation.
Sorry, I can understand what you mean.
So it's a long question, so maybe we talk after Robert.
Yeah, sorry.
Okay, so no, please again.
Just your theorem is about Coxeter groups in the space of Mark groups. And I'm wondering if for other examples of families of groups, the same thing is true, or maybe it's false.
Okay, so I don't know, but so let's say similar results showed by Koji Fujiwara and Tsurusera about the hyperbolic group, but they showed that fix the hyperbolic group G, and and take a sequence of finitely generating set of G. And if G and SK converge to the G and S, then the growth rate also converges. They showed that. They showed this result. But in this case, the group is always fixed.
Fixed, yeah.
But, so I don't know the other classes of groups. So for example, the Bohm-Sag-Solitar groups. So
yeah, I'll send you some reference. That could be interesting, I think.
Yeah. Thank you.
Okay, so we might leave further questions till after the break, unless anyone has a quick one. But okay, if there's no other quick questions, let's thank the speaker again.
Thank you.
And I'll end the recording.